in modeling when we talk about data science. The first thing is to understand the business problem. Now, this is one of the things where a lot of people do not get it right. You don't just jump into analyzing the data. You need to understand what's even the problem that I'm supposed to solve using the data. So you need to gain a clear understanding of the problem, its impact, its ultimate goal, and formulating relevant hypotheses or questions, e.g., how much, how many, which category or groups. Identify the relevant data sources is critical because you don't just jump into I just want to produce something. And I see a lot of people when they start learning this data science, they put up a lot of visualization online, which is good, but I would have preferred if they solve a particular problem and then you walk your audience through to see how you do that. But then you need to understand the problem. And that's why I said you need to have a niche. Focus on a niche. Don't just go about solving problems sporadically. Focus on a niche. Pick a niche. If you're picking a niche in business, pick a particular business problem that you want to understand. When you understand the problem, then you can be able to find a way to solve the problem. Then understanding the data. Now, this is where you need to familiarize yourself with the data. Having looked at the data sources that you need to understand this data by relating with the data. So you need a data-driven system, but you cannot do that if you don't understand the type or format of your data, the quantity of the data, the relevance of that data, and how to assess it ethically. Now, you need to realize that the real world data is very noisy. There are missing information, is inconsistent, the format varies, it comes from different sources. So it's not always whole. You will see the data looking so sparsy, you will see the data looking so messy. So you would have to do the lots of your most of the time. In fact, 80% of your time will be spent on trying to clean this data in order for you to be able to build something with it. Now, the next step is to pre-process the data. Now, having to understand your data, you need to clean it, you need to remove all the noise and all that. And via pre-processing or data exploration, we call it the EDA, you begin to summarize the data in form of statistics. What's the mean of the data? What's the standard deviations? What's the mode? What's the medium? What kind of plots or charts will you make? How do you be able to observe trends in the data? Now, how do you even build some sort of future engineering where you combine some futures in order to arrive at some other future and all that? Recently, there is a particular project that I worked on acute myocardial infarction. The paper we are currently trying to wrap up the paper. One of the things I noticed was there is a lot of sparsity in the data that I was working on because we are looking at ICD-10 code. And each ICD-10 code, we are looking at each time point where a patient accumulates these ICD-10 codes. Because at each visit that the patient goes to the GP, there is tendency the GP would identify a particular ICD-10. Well, when we talk about ICD-10 codes, these are standard nomenclature that was arrived or decided by the medical association, like World Health Organization and other bodies, where they classify diseases and diagnoses into different chapters. So that ICD-10 code for, let's say, heart diseases could be I. So all the I's, I1, I2, I3, maybe down to I90 or I99 will be different subcategories of heart complications. And then you could see things like Z could cover different things such as family history and all that. Now, such kind of analysis is like when you are looking at a branch of a tree. Okay, so you see that when you're looking at the tree from its roots up onward, it begin to spread into different sub branches. So what I did was I noticed that if I'm to work with all the ICD-10 code, which was around 1009, it will be much, and I was not getting the right signals from my model. So what I thought was maybe I should combine this chapter so that in each patient I'm going to count, if I'm looking at heart diseases, why not I count the heart diseases that was accumulated by that particular patient. So when I did that, I shrunk the futures from 1009 to around 29 of them or so. So it's like opening a book and then closing the book. So when I did that, my model improved tremendously. And I think in one of them I had around 78 or something accuracy, proud to when I was having around 50 something. So why am I saying that? You familiarize yourself with the data by performing all sort of data exploration and also feature engineering in order for you to understand if there are biases or outliers or missingness in the data, and then you find a way to clean it. So whenever you have now prepared the data in the right format, the next thing you begin to do is now to start looking at the right machine learning algorithms that you're going to use. Now, there is no right algorithm for every data, meaning that sometimes the fact that random forests work for a particular problem, when you have another problem, it doesn't mean random forest would always work. So you should not have this habit of sticking around with one particular machine learning algorithm. You have to try them. You have to try different algorithms from maybe support vector to KNN to random forest to XGBoost to LSTMs and RNNs and deep neural networks such as CNN and even generative AI models like Brett and all that, and the GPT models. So you have to try different models in order for you to come to. But that doesn't mean you go about trying everything, because some of these models have a way in which they analyze data. For example, when you are looking at the kernel models, they uses the kernel function to project this data into other dimension. So that takes a lot of computational challenges. So when you're looking, some of them becomes an NCOM problem, like the more the sample, the more the complexity increases. And that dimensional issue, gives the model a lot of headache. So you don't go about training. That's why you need to familiarize yourself with the data. Then by so doing, it will help you to prioritize the kind of machine learning models that you're going to use, and even the machine learning performance matrices that you can be using for the evaluation. For example, if you have a lot of classes, when you are having classes and then imbalanced classes is another issue, you don't go about using the normal accuracy. You have to switch to other performance metrics like F1 classifier or balance accuracy, or and so on. There are so many matrices you could use in that case. So you have to look at the problem based on the nature of the data that you have. That's what will inform the kind of machine learning algorithms that you are going to select. And then also the splitting. Sometimes people split their data. The famous one is 80-20, but I've seen where other people split into 70-30. And then I've also seen where people split into 80-10-10, meaning 10 for testing, 10 for evaluation. Then I've also seen where people split into 90-10. So again, it depends on how your data, because if your data is not much, you don't take chunk of it to the testing, because that could give rise to biasness during the training. And we'll talk about that when we begin to go deeper, because this is just an introductory class, so I wouldn't want to bore you. Then we have other model performances like the ROC curve, which is also a very